Okay, AP Calculus, we're going to get moving into section 2.7 right now, limits at infinity. And this is not going to be all that bad of a section, guys. Most students do pretty well with this one and think that it's not all that terrible. But what is interesting to me anyway, I'm not sure about you guys here, is that this is going to be one of those sections here where we realize that an idea that we have had in our head for a year or maybe even 2 years over pre-calc and algebra 2 might not necessarily be sufficient for what we really need to know about it and what we really need to be able to grasp about that concept this year. And so the big idea that we're going to be talking about here with limits at infinity is this concept right here of a horizontal asymptote. And you guys started talking about horizontal asymptotes, probably first when you saw exponential functions, which of course tend to increase at an increasing rate, but then on the other end right there, usually as x were to approach negative infinity, kind of flatten out. And this was maybe the first graph you guys saw that had a horizontal asymptote, typically right here at the x-axis. Then you saw horizontal asymptotes a lot more when you guys were talking about rational functions, which you probably didn't discuss at all in Algebra 1, but did in Algebra 2 and in pre-calc as well. So you'd usually have a vertical asymptote and you'd usually have a horizontal asymptote for your rational functions. And then normally a rational function was going to give you a hyperbola that might do something like that. Now, based on these two ideas, what you normally saw with exponential functions and then also with rational functions, you guys got an idea in your head about horizontal asymptotes that worked pretty well for you with most of the functions that you saw in the past, but frankly, isn't quite right. And it doesn't quite have the depth of understanding that you guys need that we're capable of talking about at this level. Now, I'm not sure if you guys got this wrong idea in your head because you developed it on your own, or if it's because your teachers had actually told you that's what it was. And again, let me say that that idea, which I'll get to in just a second, probably worked well for you over the last couple of years. But by the end of today, we're going to see something a little bit different. Now, that idea that most of you guys had, and it works for these two graphs, is that a horizontal asymptote is a line that your function approaches but never touches. That's what most of you guys, if I were to ask you live right now, hey, what is a horizontal asymptote? That's what most of you would probably tell me. But now that we've got a little bit more of advanced vocabulary mathematically, now that we understand some concepts that frankly we didn't understand and we weren't able to understand a year ago or 2 years ago, we've got a more complex but also a more accurate definition of a horizontal asymptote right here. Our calculus definition of a horizontal asymptote involves a limit, and this is why they didn't teach this to you 2 years ago in Algebra 2, because you guys didn't understand what a limit was, and frankly, it would have taken too long to try to explain at that point. But now that we've got it, let's talk about this. The line y equals a is a horizontal asymptote of the function f of x if the limit as x approaches either positive or negative infinity of f of x is equal to that finite value of a. And I suppose there really should be a period at the end of that sentence right there. So what we have here, guys, is kind of an if-then sentence that's kind of expressed backwards. You might have said this one to say that if the limit as x approaches plus or minus infinity of f of x is equal to a, then the line y equals a is a horizontal asymptote. That's probably the more interesting and maybe more appropriate way to look at it. But one of the things we're going to be discussing with the string of examples we're going to do here in just a second is that these concepts right here of having a limit as x approaches plus or minus infinity of your function is equal to a, and having the line y equals a as your horizontal asymptote, those two ideas are really synonymous, everybody. You could really write this here as a biconditional statement using the phrase if and only if, meaning that either one of those two conditions will cause the other. So maybe the better way to write this would have been the line y equals a is a horizontal asymptote of f of x if and only if that limit as x approaches plus or minus infinity of f of x is equal to a. And we can use either one of those ideas to our advantage in order to learn something about the other. But this concept right here, you guys, we haven't done this yet in this chapter at all. A limit as x approaches positive or negative infinity. And that doesn't sound super complicated right now, but it does add a layer of complexity, I guess I want to say, to the math that we're going to be doing in this section. And when you're trying to analyze a limit as x goes towards either positive or negative infinity, the rules that we use here, boy, they really bother some people, and other people find them really, really easy. But we need to understand that unlike every problem we've done so far, where it's been the limit as x approaches c, some constant value, infinity, negative infinity also, is not a number. And so for that reason there, the concepts that we've been using in the past about plugging in that value at some point never really apply here, because x can never equal infinity. That's really just a symbolic notation we use to indicate that x is either increasing or decreasing without bound. So we've got to do some of what I call fuzzy math in this section here, guys, but we'll see where that pops up. Now, the first thing we're going to talk about now are the rules for horizontal asymptotes. Remembering, everybody, that a horizontal asymptote is really the same thing here as a limit as x approaches either plus or minus infinity of your function. And and by the way, these rules that we're going to talk about on this page are just applicable to rational functions. So I'm hoping you guys already recognize what it is that we're talking about, because this is something that not only did you learn 2 years ago in Algebra 2, not only did you probably see it last year in pre-calculus as well, but we talked about these rules back in Chapter 1 when we were reviewing some concepts from pre-calc that we thought would be good to discuss before we got started. If I had to guess, guys, I would have said section 1.3, but please don't quote me on that without looking that up. So what's going on here? F of x, our rational function, is defined as the quotient of two polynomial functions. And all we've bothered to write here was the first or the leading term of each of those polynomials. A times x to the m power plus, and then there's just a whole bunch of junk that may or may not come after that term. And in the denominator, we're dividing by b times x to the n power. And again, there may or may not be other terms that come after that. Okay, so the three cases here, the three rules for horizontal asymptotes, all involve the relationship between m and n. And if we go back up and look at what we just wrote here, m is the exponent, or in this case, the degree of the numerator, and n is the highest exponent or the degree of the denominator. So it's always a question of degrees, everybody, and here we go. And I feel like I'm writing this in the opposite order of the way we presented it back in Chapter 1, but obviously it doesn't matter. These rules are true regardless of which order I write them in. If m is greater than n, if your exponent on top is greater than the exponent down here on bottom, that's what we informally like to call a top-heavy rational function. In that case, everybody, we have no horizontal asymptote. Now, this happens a lot, everybody. Anytime you've got yourself a function that looks like something like, how about just something like f of x is equal to x cubed? Actually, I'm just going to stop right there. There you go. The degree of your numerator is 3. Since the denominator doesn't have an x, we would say that's a degree of 0. So this is the case where m is greater than n, and a polynomial function like this, as you think about it, has no horizontal asymptote. We know what this graph looks like, everybody, and in fact, all polynomials have this property here, that as x approaches infinity, off to the right, or as x approaches negative infinity off to the left, your function either increases or decreases without bound. And that kind of supports the idea that there is no horizontal asymptote in a polynomial function. You do sometimes end up with slant asymptotes, or it can even get worse. You can have weird things like parabolic asymptotes in this case right here, but those are not a limit as x approaches infinity or negative infinity. So what we have written here is correct. There is no horizontal asymptote when the degree of your numerator is greater than the degree of your denominator. Case number 2, if m is less than n, if you have what's considered to be a bottom-heavy function, guys, in that case right here, we have a horizontal asymptote at the line y is equal to 0. And a case for that might be something put very, very simply, guys, like f of x is equal to 1 over x. That's probably the simplest rational function that you guys know. And what do we have here? The degree of your numerator is 0 because it's constant. The degree of your denominator is 1. So m0 is less than n, which is 1. And the graph, which I'm hoping you guys just have memorized here, does have a horizontal asymptote at y equals 0, or the x-axis. This one also happens to have a vertical asymptote at the y-axis. And this graph does something like this. It's a hyperbola that exists in the first and the third quadrant there. Okay, and as we can see then, knowing that graph as we probably should, we do have a horizontal asymptote at the x-axis. The third case is the most complicated of the three, but still isn't really that bad. If the degrees of your numerator and denominator are exactly the same, then in this case, everybody, we have a horizontal asymptote at the line y equals, and let me check my notation right here, yep, it is going to be a over b. And the a and the b, if we go back to this definition of what our function is right here, a is the leading coefficient of your numerator, and b is the leading coefficient of your denominator. And I'm contractually obligated to remind everybody, leading does not necessarily mean first. Leading means the coefficient of the highest degree term. Now, when we write polynomials, such as our numerator and our denominator here, in standard form, the way we're normally supposed to write them, those usually do become the first couple of terms that are out there. But you might see something like this from time to time, everybody. You might see something like f of x is equal to, and I don't know, just to make things interesting, what if I did something like a 5 minus 3x squared, let's not make that a 3, let's make that a 5 minus an 8x squared, and then down on the bottom I'm going to go with a 4x squared plus 3, something like that. So just to be clear here, in that example that I just wrote, the leading coefficient of the numerator isn't 5, it's negative 8. Because the x squared is the highest degree term in the numerator. So in this case right here, guys, your horizontal asymptote would exist at the line y equals. Okay, our a value here would be negative 8. Our b value would be a 4, and we'd end up with negative 2 there for our horizontal asymptote. Interestingly, the way that I wrote this function, I believe we are not going to have a vertical asymptote or a hole there, so that's kind of a weird graph that I would have given you there. So anyway, let's not worry too much about that. So those are the three rules, everyone here, for horizontal asymptotes of rational functions. Hopefully nothing is new here that you didn't already know, but the big idea here today is that those concepts for horizontal asymptotes also allow us to figure out a limit as x approaches plus or minus infinity. And that's really the question that we're dealing with here in all of Chapter 2. What is the limit of this function? And specifically in this section, 2.7, what's the limit as x approaches plus or minus infinity? So for most of our examples that we're going to be dealing with here today, guys, that's what's going on. I'm going to give you a function. Most of them are going to be rational, but not all of them. And we're just asking these two questions right here, everybody, which we've been asking all chapter. What is the limit of this function? Today, as x approaches both first infinity, right here, and then negative infinity. Okay, and there's a reason I'm asking this as two separate questions. It really wouldn't be good form of me to write, what is the limit as x approaches plus or minus infinity of f of x? This is really two different questions that I just wrote here in blue. Sometimes those answers are going to be the same, maybe not necessarily always. So we'll just not make any assumptions and we'll see what we see here. Okay, so with this problem right over here, everybody, there's a couple of different ways of looking at how to do a problem like this, and I want to talk about both of them right here. For all the time that we've already spent here today talking about these limits right here, it's basically a question of horizontal asymptotes. So, wouldn't be the end of the world to try to graph this function right here, at least at the beginning, and seeing if that helps us at all. So what do we know about this graph? Our vertical asymptote, let me do that in red. Our vertical asymptote comes from a value of x that would make the function undefined, or make the denominator equal 0. That's going to happen at x equals 3. So I'll go ahead and put a dashed vertical line right there. Now our horizontal asymptote, let's talk about this. We have a constant on the numerator, so that's a degree of 0, a linear function in the denominator, that's a degree of 1. This is a bottom-heavy rational function, so just this function right here would have a horizontal asymptote of y equals 0. But there's a plus 4 at the end of this, everybody, that's going to shift everything on this graph up 4 units. So the circled portion has a horizontal asymptote of 0, but adding 4 to that would give us a horizontal asymptote here of y is equal to 4. Now, nobody in the world would ever do on their own what I'm about to do, but I kind of like to take the time to show you that there's another way of getting that same answer. If we were to take f of x and try to write it as one fraction, this would be negative 2 over x minus 3 plus, and if I now wanted to put these two terms together, I would multiply both the numerator and denominator of the second term by x minus 3. Now, let's see what happens there. What are we going to get? We're going to distribute that 4 right here to get a 4x minus 12. We're going to combine that with the negative 2 from the first numerator and get 4x minus 14 all over x minus 3. And if we were to consider this form of the rational function, now take a look at your degrees. First degree on top, first degree on bottom, it's a tie. So in this case, your horizontal asymptote would come from the quotient of your two leading coefficients, which is a 4 on top and a 1 on bottom, and 4 divided by 1, last I checked, is 4. So we get the exact same result regardless of whether we leave it in, this form up here on the top is what a lot of Algebra 2 textbooks kind of introduce as like the first form of a rational function, or if we went ahead and wrote the whole thing out. Now, if I cared about the graph, which I've come this far, so I want to go ahead and get it right, I would go ahead and test a couple of values to the left and to the right of the vertical asymptote to figure out which quadrants this graph is actually in. So I'd probably put in something to the right of x equals 3, so I'd probably put in 4. And if I did that, that's a negative 2 over 1, which is negative 2 plus 4, which is going to be positive 2. So I get the point 4, 2 as a point on this graph. That tells me what I need to know, guys, because I understand what asymptotes do. I'm going to think that this graph looks something like that. And right there, everybody, what do we see? We've got the answer to this first question right here. The limit as x approaches infinity of this function is, well, let's use the bouncing green dot here, everybody. We'll go with that one. And as x increases without bound, as it approaches infinity, our y value seems to be approaching the value of our horizontal asymptote, which is 4. Now, if Mr. Fontana were in charge of the entire world, I might ask you guys to do this. And if you think about what that means, you might understand it because we've seen that with limits here. What I would mean by this, don't guys, I can't make up my own notation and we're going to erase it in just a second, but I would take this to mean that as x approaches infinity, y is approaching 4, but from underneath that value, meaning that our y values are all going to be less than 4, but are moving up and getting closer and closer to it. But again, can't just make stuff up here, guys. All right, anyway, and then how about the other half? Well, I'd now put in an x value that was less than 4, and probably the easiest one to do there would be 0. So if I put a 0 in for x, everybody, that's negative 2 over negative 3, positive 2/3, plus 4 is 4 2/3. Gets me a blue dot right about there, and again, knowing what I know about asymptotes and rational functions, I think this graph is going to look something like that. And now we're able to answer the second question. What's the limit as x approaches negative infinity now of this function? So I'd move my green dot over here, and oh, that's not what I wanted. I'd move my green dot right here, there we go, and as I move right to left, as x is decreasing without bound and approaching negative infinity, my y value seems to be approaching 4 as well. Now this time, I would have put a plus after that, meaning that it's approaching 4, but from above, and it's working its way down. But again, we don't get to do that. So let's look at all of this in its entirety, everybody. And I'm saying this as much for my own benefit as it would be for yours, guys. And here we go. You need to keep in mind, what were we given at the start of this problem? That was all of this right here. So let me clear out some of the extra junk that I've put in there. All right, so this is what we were given. And then these are the questions that we were asked right here. What are the limits as x approaches positive infinity and then negative infinity? And I certainly did more work on this problem than you guys are going to need to do. If you can look at this rational function pretty quickly and realize that that limit in both spots, or that asymptote, is going to be 4, then you've already answered the limit question. So a lot of the work that I did right here was to try to help us get a better understanding of what was happening here, but it's not work that's going to be necessary for you guys to show. All right, so keep that in mind. And the one thing I wanted to point out here, I'm not making any declarative statements here yet, but our two limits were the same. All right, let's move on to another one right here. Okay, this is a function that I gave you guys a while ago, -1 over x plus 2 quantity squared. So let's see what happens with this one. Okay, as we think about horizontal asymptotes, this is probably the way we should be approaching it right here. As we think about that, we have a constant in the numerator, and then what's really a second degree function down in the denominator. So this is a bottom-heavy function. And in a bottom-heavy function, you always have a horizontal asymptote at y equals 0. That right there, guys, if you think you know what's going on with a rational function, really should be the answer to this question. I think we're going to get this approaching a y value of 0 here as we move to the right, and the same thing should happen over here to the left. Now really, that's as much work as you guys need to do on some of these problems if, let me finish this thought, if it's a rational function and you feel confident that you know how this function behaves in both directions. So that's really where we could stop. I'm going to go just a little bit further because I want to prove my point to you guys. A vertical asymptote exists when our denominator would equal 0. That's going to be x equals -2. So probably could have made that graph a little bigger. There we go. Okay, so a vertical asymptote right here at -2, a horizontal asymptote right here once again at 0 here at the x-axis. And if you weren't quite sure, you could go ahead and plug in values on either side of the vertical asymptote. For example, if we put in a 0, the denominator is going to become 4, and we get -1/4 for that. So that tells me that this part of the hyperbola exists in the lower right quadrant. And now if we were to put in a value to the left of -2, like, oh, say -3, let's see, -3 plus 2 is going to get us -1, but we're going to square that to get a +1. -1 divided by 1 is -1. So that gets us the point -3, -1, and this graph is going to look something like that. And as we look more carefully at the graph, let's think now, does the graph support or refute this idea that we came up with, that both of those limits are equal to 0? Certainly looks like in this case that it supports that concept. So again, the graphing is something you can do to kind of verify your ideas, but it is not something that is necessary for you guys to do. Boy, as I look at this graph here, you guys, it really should be symmetric with respect to that vertical asymptote. Pretty disappointed in my graph right there. I hope you guys can forgive me. But anyway, let's move on to C. Okay, still another rational function now, but perhaps a more complicated one. X squared minus 9 on top and x squared minus 4 down on on bottom. Now this one, everybody, again, trying to do it the efficient way that I would ask you guys to do, let's go ahead and have our conversation here about horizontal asymptote. The degree of the numerator is 2. The degree of the denominator is also 2. So we have a horizontal asymptote at y equals the quotient of your leading coefficients. Our leading coefficient on top is 1, and so it's the same thing on bottom. And 1 over 1, last I checked, is 1. So if we know what we think we know about rational functions, the limit as x approaches infinity of f of x is 1, and the limit as x approaches negative infinity of f of x is also 1. And that's where you guys would probably stop. But there's a risk involved there, everybody, if you're not certain that you know how this rational function behaves. So that's what I want to spend just another couple minutes playing around with right here. Partly because I want you guys to feel confident in your answer, but let me be honest, partly because I think this stuff is cool and interesting, and I want you guys to look at this as like a mathematical experiment. Like we're actually going to the lab in a Bunsen burner and we're going to find out what happens and see if our hypothesis is verified or not. So what do we know about this graph, everybody? A vertical asymptote, let's see, is a spot where your denominator would equal 0. Now that denominator, x squared minus 4, factors into x plus 2, x minus 2. So we're actually going to have two vertical asymptotes here at x equals plus or minus 2. Now you've seen graphs like this in the past, but I don't know that we've seen any this year. The fact that we have two vertical asymptotes changes things pretty dramatically from the last two functions that we've dealt with. That means that this graph is going to exist in 3 different pieces instead of just in 2. Let's keep that in mind. Horizontal asymptote right here at y equals 1. That's the only one that we came up with. So now, instead of using the word quadrants, which, let me go back a step, this graph that we drew here had one vertical and one horizontal asymptote. It cut the coordinate plane up into 4 sections, and that's what the word quadrant means. Here, with 3 asymptotes in total, 2 verticals and 1 horizontal, we've created sextants. There's a fun word for you. 1 out of 6 regions here in the coordinate plane, sextants. And this graph is going to exist, well, not in all 6. We know that for sure. So let's see what's going on here. And I'm going to ask you guys to maybe recall some things about rational functions that you may have forgotten, but let's see where we're at. The first thing I would probably do is pick a number, let's go way off to the right now, something greater than positive 2. So let's go ahead and put a 3 in and see what happens. And I'm going to write all this out. Evaluating f of 3 is going to get us, oh that's convenient, a 0 on top and a 5 on the bottom, which is 0. So we get the ordered pair 3, 0 right here. Now I think I know what rational functions do and how they behave, and I think I understand what asymptotes are for, so I believe I know that this graph is going to look something like this on that spot there. And that seems to support this answer that we've already come up with, that the limit as x approaches infinity of f of x is equal to 1. All right, let's go a little bit further. Let me put in a value way off to the left now. Let me go ahead and put in f of negative 3. Well, this is going to be fun. When I evaluate negative 3, the exact same things happen that happened just a second ago when I did f of 3. Because all of my x's, the only x's that I have in this function, are getting squared. So 3 and negative 3 are going to give us the exact same result. And I'm hoping you guys are thinking the word already before I say it. That's because this is an even function. The only exponents, or the only x's we have, all have even exponents on them. So whether we put in 3 or negative 3, or whether we put in 11 or negative 11, doesn't matter, we're always going to get the same result. So that's going to give us 0 as well, negative 3, 0. And this is a method for graphing rational functions that you guys have probably learned over the last couple of years. Try to find the zeros of your function. And we found 2 of them right over here. and I think this graph is going to look like that. And if we're right about this, everybody, that supports this second answer right here, that the limit as x approaches negative infinity of f of x looks like it's 1 again. Now again, if I were doing my little addendum trick, this would be approaching 1 from the left, or excuse me, from underneath. This would be approaching 1 from underneath as well. But again, can't do that. Now, we've answered the limit questions, so we really are done. But I would be remiss, everybody, and I wouldn't respect myself if I didn't talk a little bit more with you guys about what the rest of this graph looks like. We haven't picked any x values in between the two vertical asymptotes. So let's go ahead and do that real quick just to get a better picture of what's going on right here. Obviously, we'd want to pick 0. That's going to get us a -9 over a -4. That's just going to be positive 9/4, which is 2 1/4. All right, so right about there. If we were to pick f of, and what I think we've learned here, guys, whether we do positive or -1, we're going to get the exact same result either way. Let's see what that's going to do for us. That's going to be 1 minus 9, which is a -8 on top, and give us a 1 minus 4, which is a -3 on bottom, and that's going to give us a positive 8/3, which, careful here, f of 0, 9/4, was 2 1/4. This one now is 2 2/3. It's a little bit higher than that. So 1, 2 2/3, -1, 2 2/3. And the orientation of those 3 points, everybody, I'm hoping gives you a sense for what this thing looks like. We could find it in a little bit greater detail, but that would involve using non-integer values, and I don't think that's probably worth our time. But this graph has, oh, and I want to be really careful here, guys. This graph has kind of a U shape to it right up here in this top middle sextant. And the word I intentionally did not use that I think is on all of your lips right now is parabola. That graph looks like a parabola up in that top middle section. It is not. I didn't say that on purpose, because parabolas are not bounded on the sides by vertical asymptotes. Parabolas, as they move away from the origin, continue to get wider and wider and wider. So a true parabolic function up here on top would probably look something like this, and it would continue to spread out to the right and to the left. This thing that we drew, everybody, is never going to get to a width of what? 4 units right there, which is the distance from -2 to +2 between your two vertical asymptotes. So you can say that it's U-shaped, but you really shouldn't use the word parabola. Now, with all of that in mind, okay, that's a pretty complete graph, and I think that the graph here supports the ideas that we came up with right here, and once again, our limits as x approaches positive and negative infinity both ended up being the same yet again. Okay. I swear there's a reason I'm doing this here. I don't mean to just beat the idea to death with you guys here, but I want to do, I think, one last rational function before we move on, into some inverse trig, some exponential, kind of a combination of trig and polynomial, and then that radical function. So let me do one more with you here and see where we're at with this one. Now again, just looking at the two questions right here, it's really just a question of horizontal asymptotes. And that's going to occur at y equals, well, let's take a look. Second degree on top, second degree on bottom. The leading coefficients are 1 and 1, so I think we've got a horizontal asymptote at y equals 1, which means we've got a limit here of 1 and a limit here of 1. And I think we're really done with the problem. But now for fun. All right, vertical asymptote at x equals, again, the denominator would equal 0 at plus or minus 2. There's a reason I gave you something similar to the last one. You'll see why. Okay, got that. We only have one horizontal asymptote, again, at y equals 1. So, not an accident. At this point, this graph in D looks exactly like the asymptotes that we set up here in C. Let's see what happens next, everybody. If we were to put in 3, and this one is not an even function, everybody, because of the presence of the 3x there. And of course, that's x to the first power. So that tells us something important. When I go ahead and put in f of 3, I'll get some result. When I get f of -3, I'm expecting a different result. than what I got from f of 3. Okay, so plugging a 3 in there on the top, that's going to be a 9 minus 9 minus 4. That is negative 4. And down on the bottom, 9 minus 4 is going to be 5. So we get the point 3 and now negative 4/5. Now, once again, I think I understand what asymptotes do to a rational function. I think that's what this graph looks like, and that supports that answer right there. Let's go ahead and put in negative 3. Now, we're going to have 9 again, but that's going to be a 9 plus 9 now, which is 18 minus 4 is going to be 14. Now, the denominator, the x squared minus 4, that's even, so that's going to get me the same result of 5. All right, so with negative 3, we get what, guys? 2 4/5. So negative 3 and 2 4/5 is right about there. I think I know what this thing does, and I think it looks something like that. Okay, now what happens in the middle? When we would go, and what I would think most of you guys would probably do is think about f of 0 is going to get you okay, right away here it happens. We get a negative 4 on top, we get a negative 4 on bottom, and that quotient is 1. The significance of that happens, and you might see it now, when I go to plot that point, 0, 1, right there. The preconceived notion that a lot of you guys have already about horizontal asymptotes has just been disproven. The pre-calc definition that a lot of you guys walked in here with, I said earlier, of a horizontal asymptote is a line that your function approaches but does not touch or does not cross. Right here, you guys, with the existence of that one point, it is squarely located on the horizontal asymptote. And that tells me that at a minimum, this function touches its horizontal asymptote, and maybe even more than that, maybe it actually crosses the horizontal asymptote. The other thing I wanted to do real quick, other than just plugging in points, let's talk about this real quick, guys. The original function, f of x, I believe I gave you quadratic expressions on both the top and the bottom that can both be factored. Obviously, we had an x plus 2 and an x minus 2 on the bottom, but on the top, that's going to get us an x minus 4 and an x plus 1, if I'm not mistaken. I believe that's correct. What that tells us, everybody, is that f of x will equal 0 when either x minus 4 or x minus 1 is equal to 0. So this function has a 0 or a root or an x-intercept at x equals positive 4, 1, 2, so it should have been right there that I passed through, I was close, but also a 0 at x equals negative 1 right over here. Okay, that didn't entirely do what I was hoping it would do, but all right. So we've got that in mind, and I tell you what, guys, I hate to throw one more at you, but just for fun, I'm going to go ahead and evaluate f of 1. Which is another spot in between the two vertical asymptotes. So putting a 1 up here, that's going to be a 1 minus 3, which is negative 2, minus 4, that's a negative 6 on the top. And on the bottom, 1 squared minus 4 is negative 3, which equals 2. So if I plot the ordered pair 1, 2, now I'm hoping you guys look at those 3 points in between the vertical asymptote and all of a sudden have this moment of realization when you go, oh yeah, I remember seeing some rational functions in the past that do this. Everybody, vertical asymptotes do what they normally do, but this function in the middle looks something like that. Almost looks like, actually looks very much like, one cycle of a tangent function. With vertical asymptotes bounding it on both sides, it's just shifted up 1 unit. And the reason I took so much time to graph this function properly, you guys, is because it disproves the notion that a lot of you guys had, that a function can't cross its horizontal asymptote. Clearly here, it can. This would be a counterexample that disproves the statement that a function can never cross its horizontal asymptote. The important thing here, guys, horizontal asymptotes aren't values that your function can never reach. They usually can, but normally they're at relatively small values of x. We are interested today in what happens as x increases without bounds or as x decreases without bounds. Okay? All right, so that's where we're at on D. All right, speaking of tangent graphs, which I mentioned just a second ago, let's play around with inverse tangent for just a second. And there's a reason that I'm giving you this here, and let's see what we remember. Okay, real quick here in green, if we recall what the graph of y equals tangent of x looks like, it's got a vertical asymptote at pi over 2, which is roughly 1.5. It's got another vertical asymptote at negative pi over 2, right over here. Tangent of 0 is 0, and then this thing takes a shape a lot like what I just showed you a moment ago, where it shoots through the origin with a slope of 1 and kind of curves upward here on the right and downward here on the left. That is just one cycle of the tangent graph, everybody, and it repeats itself ad nauseum. If we wanted to come up with the graph of inverse tangent of x, all we do is take this entire graph and reflect it across the line y equals x. So what does that mean? All of our vertical asymptotes on the tangent graph now become horizontal asymptotes. And the significance here is that this graph has a horizontal asymptote at not x equals pi over 2 now, but y equals pi over 2. But the really interesting thing is it has another horizontal asymptote at y equals negative pi over 2. We haven't seen a function yet today that has two different horizontal asymptotes, but this one does. So at positive pi over 2, there's one of our horizontal asymptotes, and at negative pi over 2, here's the second one. Now again, there are more, but usually when we graph an inverse tangent function, we just do the one cycle. We started graphing tangent at 0, 0. Invert that ordered pair, switch your x's and y's, and you end up at 0, 0. The rest of that green function moved up into the first quadrant, where where x and y values were both positive, but for example, most of these points had a small x value and a pretty high y value. Now when we invert those, positive, positive inverts into still positive, positive. But when we went small x and big y, that gets now inverted into big X and small y values. That's going to put us out here somewhere, and I'm hoping that tells you guys what you need to see, that that graph does something like that. Let's take a look. The other part of the green tangent graph was in the third quadrant, negative, negative, which inverts into negative, negative again. But here, we were talking in terms of absolute value, small x and big Y. Now that inverts into big X and small y. So that's going to put us out here somewhere, and that graph is going to look something like this. So what we have in blue there, everybody, is the graph of f of x equals inverse tangent of x. And now that we've seen that, for the first time today, let's take a look at these two questions. First, the limit as x approaches positive infinity of this function. As x pushes further and further out to the right, our y value, following the blue track, if you will, is getting closer and closer to a y value of pi over 2. But as we look to the second question now, as x is approaching negative infinity, let me put my green dot here, I should have done that a second ago. As x is approaching negative infinity, our y value is decreasing and approaching a y value now of negative pi over 2. So for the first time today, everybody, we now see a function that has different limits as x approaches infinity and as x approaches negative infinity. And that goes hand in hand with the concept that this same function here has two different horizontal asymptotes. So we hadn't seen one yet with multiple horizontal asymptotes, and now we have. If I take you back to the last two problems, we saw functions that had two vertical asymptotes, and a question I might have asked if we were talking about this in a previous class, could you have three vertical asymptotes? The answer is yes. All I'd have to do is put another factor down here on the bottom, like x plus 7, and now x equals negative 7 is a vertical asymptote. So a function can have as many vertical asymptotes as we wanted it to have. Now, try to apply that same reasoning. Can a function have more than one horizontal asymptote? Obviously, yes it can, just maybe not a polynomial. Now the next follow-up question would be, can a function have multiple horizontal asymptotes? And by that I really mean more than two. The answer to that is no. The only way that a function has a horizontal asymptote is if it has a limiting value as x approaches either positive infinity or negative infinity. There's only two directions that it can move to infinity, guys, either to the right or to the left. There's no third limiting value right there. It's either going off right or to the left. So we're always going to have a maximum of two horizontal asymptotes. All right, this is a pretty simple one here, guys, and I'm wondering if you couldn't answer these questions without even drawing the graph, but let's go ahead and do it. We know that an exponential growth function such as e to the x has a horizontal asymptote, only one, as we move out in both directions. So a lot of people are going to think about that and say, okay, in the previous problems that I did, like for example, example A, let's go with that one right here. There was only one horizontal asymptote here. That was 4, and that was the answer to both of these two questions here. So I could understand if you thought about this graph here without graphing it and said there's only one horizontal asymptote. Let me go ahead and write that out. Horizontal asymptote at y equals 0. Therefore, that's the answer to both of these two questions. I can see why you might think that. But I think you guys already see the problem with this if you think about what it is that you are saying. The graph of e to the x is one you guys certainly should have memorized by now, and it looks something like this. So one of these two answers that we've written down is correct. It's this one right here. The limit as x approaches negative infinity, let me do a green dot here. The limit as x approaches negative infinity. As x decreases without bound, our y value is getting closer and closer and closer to a y value of 0. But the problem is right here, guys, on the first question. As x increases without bound, as x moves from left to right, what y value is our function approaching? It's not approaching a finite value. It is increasing without bound. So I want to talk about the difference here right now, guys, between two things that a lot of you think are the same and are not. It would be incorrect here, everybody, to write that the limit does not exist. We reserve does not exist, everybody, for the idea when two one-sided limits disagree with one another, or when a value doesn't approach or doesn't converge towards anything in particular, but just oscillates back and forth. So this is not correct for what we're doing here. What is going on in this problem, everybody, is that as x approaches positive infinity, our y values are increasing without bound, so that's when we would go ahead and put an infinity there for that limit. That is different than saying that the limit does not exist. So we need to be careful right here. Even though we only had one horizontal asymptote to this function, that value, 0, was not the answer to both of these questions. Exponential functions behave differently than rational functions. That's the important thing to understand from this example. All right, another one that I wanted to talk about with you guys is this one right here, sine of x over x. And this is a fun one for me, guys, because this actually proves another point here that we might not have thought about before. So we saw this graph back in, I think just in 2.5, right? No, 2.6 when we were doing trig limits here. And as we drew the graph, what we found was that the limit, in fact, let me write this out, the limit as x approaches 0 of sine of x over x, we did a little analysis on and we figured out that that limit was 1. Although clearly the function is not continuous at that spot. So it's got an open dot right here at x equals 1, and I don't care that much about the graph, but roughly pi over 2 pi 3 pi over 2, something like that. And this graph is going to kind of have a decreasing amplitude as it goes on and do something like this. I'm not super worried about this graph. If I was, I'd probably do it on my calculator, but it looks something like that. And that's the graph of sine of x over x. I described it as being like a cosine wave, but with a decreasing amplitude as we get further and further away from the y-axis. So what's interesting about this problem here, everybody, we can't apply any of the tricks that we've learned before for how to figure out your horizontal asymptote. We really just need to look at the graph and ask ourselves that as x approaches infinity, what is happening to the value of the function itself? Well, I couldn't help myself, and I started talking about this a little bit in 2.5. The numerator, sine of x, as x approaches infinity, that value on top is going to bounce back and forth between +1 and -1. It'll equal 0 every so often, right? At every pi units right there, but it's never going to get very big. The denominator, on the other hand, increases without bound. So as x approaches infinity, we're dealing with a numerator that always stays relatively small in terms of its absolute value, and a denominator that gets huge. What does that do to the value of our fraction? It makes it get lower overall, and when the bottom of a fraction has a growth rate that outpaces the numerator, the value of that fraction ends up approaching 0. And that's what happens here. Okay? The limit as x approaches infinity of this function is going to equal 0. And as we look at the second question, the limit as x approaches negative infinity, the exact same thing happens here, and we end up with 0 as well. Without dwelling on this for too long, you guys, what I find interesting and noteworthy about this example is it shows that not only can a function equal or reach its horizontal asymptote, this function actually does so an infinite number of times, at pi over 2, and at pi, and at 3 pi over 2, and at 2 pi, and so on, and so forth, and forever and ever, amen. This thing does this over and over and over again, but we can see that overall, the amplitude of this thing is shrinking, and that's why our limit on both sides is 0. And the last problem I wanted to do with you guys today, I pulled this one right out of the book. This might actually be a homework question. It probably is. Let's go ahead and talk about 2.7, number 23. And when I said a long time ago, sorry guys, that limits at infinity involve a little bit of fuzzy math, this is the one that I'm talking about. So how in the world are we supposed to do this problem, Mr. Fontana? Because I don't know how to graph this function right here. We've never talked about something like this before. How am I supposed to do it without just going to my calculator and getting the graph that way? Well, I'm going to show you guys, but like I said, this is the fuzzy math that a lot of people don't like. The fact that we are doing a limit here as x approaches infinity says something really important. We're thinking about x values that are really, really, really big, not just in the tens and the hundreds, but the thousands and the millions and the billions. So I want to ask you guys about that term right there in the denominator. 4x cubed plus 1. My question for you guys is that 1 significant? Does it contribute something important to the overall value of the function? Or is it, and here's a great word, negligible? Is it something that we can get away with ignoring? Well, that plus 1 is really significant when the value of x is small. But as the value of x approaches infinity and gets into the thousands and the millions and the billions, the impact overall of that plus 1 on the function really becomes less and less and less important. So the fuzzy math that we're allowed to do, you guys are going to love this, is because we're doing a limit, let me say it again, as x approaches infinity, a huge number, we get to ignore that plus 1 and really just focus on the 4x cubed as the only important term in the denominator as x approaches infinity. And the exact same rationale, you guys, works in the numerator. The value of this plus 2 is significant and important when x is really, really small. But because we're talking about x approaching infinity, the value of that plus 2 becomes less important to the point where it is negligible and we can ignore it. And by the exact same rationale, the exact same thing happens with this middle term of 3x. Compared to the value, the relative importance of the 9x to the fourth, the value of that 3x isn't much either. That term is negligible as well. So I'm going to write something mathematically that I don't think you guys are going to like, but it's correct. This limit expression, in fact, let me move all of this down here, guys. This limit expression, oh boy, here we go, is equal to, and I didn't say equivalent, I didn't say approximately, it is equal to the limit as x approaches infinity of just the leading terms, which would be the square root of 9x to the fourth up on top, ignoring the other two terms, and just the 4x cubed down here on the bottom. Now I got to be very clear with you guys. I'm going to grab my eraser, don't do this in your notes. If I erased that, and if I erased that, this is no longer a true statement. You can't just wipe out 3 terms because you don't think they matter. So right now, this is incorrect. The function on the left is not equal to the function on the right. It doesn't give you the same value. But when we're talking about limits, everybody, this is fuzzy math. And this statement is correct now. These two things have the same limits because as we're talking about a limit as x approaches infinity, x is getting so big that we can ignore these 3 terms here and just focus on this. So where do we go from here? Well, it's not that bad of a problem now. This is the limit as x approaches infinity of, and, oh, what a coincidence, 9x to the fourth is a perfect square. So that square root is 3x squared over 4x cubed. Now it's a simple rational function. It's bottom heavy. The degree of the denominator is greater than the degree of the numerator, and that means that we have a horizontal asymptote here at y equals 0. And your horizontal asymptote is your limit as x approaches infinity. So this answer is 0. That type of reasoning here is different than what you guys have done over the last umpteen years when you've been trained very carefully not to just ignore terms and certainly not to just cancel something out because you didn't like it being there, but because we're doing something different here, a limit as x approaches infinity, we're not dealing with a finite number. These don't have to be exactly right. We're just talking about the overall impression here as x increases without bound. So you'll see a few problems like that on your homework, everybody, and I want to stress what we did in this problem only works because x is approaching infinity. Okay, it would work with negative infinity too, but if I put in a finite number like the limit as x approaches 5, okay, I could not do what I just did right there. This only works because x is increasing without bound and those other terms become negligible. That's the word of the day there for that, everybody. Okay, that was a long talk right there, but that's a wrap on 2.7. So let's give that homework a try and let me know if you guys have any questions on it. Good luck.